This video provides easy-to-follow instructions for you to create and animate this fidget spinner using Onshape. Click below in the video description. Here you will find links to all of the resources you need to complete this project. First, there is a link for a PDF instruction sheet. Click this link and open the project drawings and specifications in a new browser tab. Next, if you don't have an Onshape account, use one of these links to create a free account at the Onshape website. Last, there are links for each of the segments of this video. The video instruction is organized into 5 segments. In segment 1, you will create the bearing. In segment 2, you will create the spinner. In segment 3, you will create the hub. In segment 4, you will assemble your fidget spinner using mates. In segment 5, you will animate your spinner to view its operation. So, now you are ready to begin the project. In this first segment, we'll create the bearing. The 608 ball bearing is a commonly manufactured part used for skateboard wheels and fidget spinners. If you were to 3D print your spinner, this bearing is probably what you would use to make it spin. For our model, we only need to create a simple placeholder part that has the same dimensions as the actual bearing to use in our assembly. Let's look at the engineering drawing of the bearing. First, there is an isometric view to help us visualize the part in 3D. There are also 2 orthographic views. These are displayed as flat drawings and used to communicate the shape and size information. In the lower left corner is the front orthographic view. Aligned above the front view is the top view. To create the model of the part, we need to identify its basic shapes. The top view shows the part is circular. The front view shows that it has a flat, uniform thickness. The top view shows a circular hole through the center. The front view shows that this hole goes all the way through the part. Next, let's read the size dimensions. The outside diameter is 22 millimeters. The hole has a diameter of 8 millimeters. The thickness is 7 millimeters. I've started a new Onshape document and named it Fidget Spinner. First, let's check the document's workspace units. I want to make sure that length is set to millimeters and mass is set to grams. Use the green check to close. Start a new sketch by clicking on the button in the toolbar. Click on the top sketch plane to choose it. Right-click and choose View Normal to the sketch plane. Use P on the keyboard to turn off the visibility of the sketch planes. From the toolbar, choose Center Point Circle. Click coincident to the origin to set the center and then click again to create the circle. From the keyboard, enter 22 millimeters for the diameter. Click again on the origin to create the inner hole. Set the diameter at 8 millimeters. Right-click the mouse and choose Escape Circle to end the command. The sketch is complete, so use the green check to accept the sketch. Right-click again and choose Isometric View from the menu. Next, from the Feature toolbar, choose the Extrude tool. This will be new. For the region, choose the sketch. Use the checkbox to extrude symmetric. Set the depth to 7 millimeters. The part will be centered and extend equally above and below the top sketch plane. This looks correct, so use the green check to accept. We have now created the bearing. Looking in the feature list, you can see that Sketch 1 and Extrude 1 are listed. If you need to edit either feature, you can double-click to open it again and make changes. In this segment, we'll create the spinner. Let's start by reading the engineering drawings. First, the drawings show an isometric view. This helps us visualize the part in 3 dimensions. 2 orthographic views are also provided. In the lower left corner is a front view, and aligned above the front view is a top view. To help in making the model, we need to identify the shapes and features that make up the part. The spinner contains a number of circular features, all concentric to a common center point. At the center is a solid circular shape. Evenly spaced around the outside are 3 equally sized circles. At the center, there's a circular hole, and the front view shows that it extends through the part. There are 3 additional holes, each located at the center of each of the outside circles. and these holes extend through the part. The front view shows a uniform thickness with rounded outside edges. Next, let's read the dimensions. The central hub has a radius of 19 millimeters. This makes the diameter 38 millimeters. The three outer circles have the same diameter of 38 millimeters. The centers of all of the outside circles are coincident to the circle center with a diameter of 50 millimeters. This makes the center of the outside circles 25 millimeters from the center of the part, and evenly spaced around the center. The center hole and all of the outside holes have a diameter of 22 millimeters to fit the bearing. The part has a thickness of 7 millimeters, and the top and bottom outside edges are rounded with a 3.5 millimeter radius fillet. In this segment, we're going to create the spinner. I've opened my Onshape document named Fidget Spinner. I can see that this document already contains a part studio with the bearing. To create the spinner, we are going to need a new part studio. Click on the plus in the lower left corner and choose Create Part Studio. We have now created and opened a new empty part studio for our spinner. Start by clicking on the Sketch button on the toolbar. Click on the top sketch plane to choose it. Right-click and choose View Normal to the sketch plane. And use P on the keyboard to turn off the planes. I know from the drawings that the center has two circles, with the smaller one to fit the bearing. Choose Center Point Circle from the sketch tools and click on the origin for the center of the circle. Click again and then set the diameter to 22 millimeters. Next, again click on the origin for the center of the larger circle and click to create a circle outside the smaller one. Enter 38 for the diameter. Right-click and choose End Circle. To create one instance of my outer circles, I'm going to use a construction line to locate their center point. Click on the Line tool and then the Construction tool in the toolbar. Click on the origin to start the line and pull it vertical above the existing circles and double-click to end the line. Enter the length as 25 millimeters. We can now draw the outer circles using the end point of this line as the center. Click on the Center Point Circle tool and click on the end of the line. Click again to make the first circle. Click on the end point again for the center of the larger circle. Click again and then right-click and end the circle tool. These two outer circles have the same diameters as the first circle, so we will use and equal constraint to set their size. From the constraint tools, choose Equal. Click on the bearing circle and then click on the circle above it to make it the same size. Click on the larger circle at the center and then the larger circle above. They should all turn black, showing that they're fully constrained. And now if I were to change the diameter of either center circles, these outer circles will change with them. The drawing shows that there are 3 instances of these outer circles. To create the additional circles, we're going to use a Circular Pattern tool. Choose Circular Pattern from the toolbar. Click on the outer circles to repeat them. You can see the instances automatically created and evenly spaced about the center point. There are 3 instances. You could edit this to create more. 240 degrees is the included angle. This means there are 120 degrees between each instance of the pattern. This could also be changed by dragging the arrow. I want to keep the even spacing. Click the left mouse button to accept the pattern and end the command. Looking at the new circles in the pattern, I can see that they are blue, indicating that they are not fully constrained. With the mouse, click on a blue circle and drag to determine its degrees of freedom. Notice that the center of the pattern moves and is not constrained. Choose Coincident from the constraint tools. Click on the pattern center and then the origin. All of the entities should now be black and fully constrained. The sketch is complete. Use the green check to accept. Right-click and choose Isometric View. Choose Extrude from the Feature toolbar. This will be a new part. Set the depth of the extrusion to 7 millimeters. Check the box for Symmetrical to extrude equally above and below the top plane. Click on the regions of the sketch that will be included in the spinner. If you click on a region that you don't want, click on it again to remove it from the selection. Use the green check to accept. Next, we're going to round over the top and bottom outside edges. Click on the fillet tool in the toolbar. Set the radius to 3.5 millimeters. Start by clicking on the small faces between the larger outer circles. Next, click on the outside faces of the larger circles. This should result in all of the outside edges being rounded. Use the green check to accept, right-click and go to isometric. We have now completed the spinner. In the parts list, right-click on Part 1 and choose Rename, enter Spinner. In the Part Studio tab, right-click and choose Rename the tab, enter Spinner. Also, we will change the appearance of the part. Right-click on the spinner in the parts list and choose Edit Appearance. Choose red for its color. Use the green check to accept. In this segment, we'll create the hub. Let's start by reading the engineering drawings. First, there are two isometric views provided to help visualize the part in 3D. Also, there are three orthographic views. In the lower left corner is a front view. Projected directly above the front view is a top view. Projected to the right of the front view is a right side view, shown here as a half-section view of the hub. Before modeling the part, let's identify the basic shapes. The hub is circular and symmetrical. All of the features are concentric to the center. It has a circular shaft that extends below and fits into the center hole of the bearing in the assembled fidget spinner. There's a thin shoulder or standoff that will provide a clearance between the hub and the spinner. The top cap of the hub is also circular and concentric to the center. The top surface of the hub has a circular recess that is also concentric to the center. The top outside edge is rounded with a fillet. Next, we'll review the dimensions. The diameter of the shaft is 8 millimeters. The diameter of the standoff is 12 millimeters. The thickness of the standoff is 0.5 millimeters. The outside diameter of the cap is 22 millimeters. The thickness of the cap is 3 millimeters. The total height of the hub, including the cap and the shaft, is 7 millimeters. The center recess has a diameter of 18 millimeters. The arc that forms the recess in the center has a radius of 28 millimeters. The rounded top edge has a radius of 2 millimeters. In this segment, we're going to create the hub for our fidget spinner. To begin, let's review the steps we will use to create all of the features. We'll start with a sketch that includes the diameter of the shaft and the standoff. Using the extrude tool, we will create the shaft and the standoff. Next, we will use a sketch to create half of the profile needed for the cap portion of the hub. Then, using a revolve tool, we will create the cap. Lastly, add a fillet to round over the top outside edge. I've opened up my Onshape document named Fidget Spinner. This document already contains part studios with the bearing and the spinner. For the hub, we will create a new part studio. Click the Sketch button on the toolbar. Click on the top plane to select it. Use N on the keyboard to view normal to the sketch plane. Use P on the keyboard to turn off the visibility of the sketch planes. Click on the center point circle from the toolbar. Click Coincident to the origin and create an 8 mm circle for the shaft. Click Coincident to the origin again and create a 12 mm circle for the standoff. Use Escape on the keyboard to end the circle. Use the green check to accept the sketch. Right-click and choose Isometric View. Click on the Extrude tool from the Feature toolbar. Click on the inner circle to create the shaft. This has a total depth of 4 millimeters. And it should extend down below the sketch plane. Use the green check to accept. Now we're going to add the standoff. Click on the Extrude tool again. Click on Sketch 1 in the feature list to turn on its visibility. Set the depth at 0.5 millimeters. And click on the center circle and on the outside circle. Click the arrow to change the direction to extend below the sketch plane. Use the green check to accept. These features represent the bottom portion of the hub. We need to add the round upper portion that will be the cap with a recessed center. Use the Sketch button on the toolbar and from the feature list click on the front sketch plane. Use N on the keyboard to view normal to the sketch plane. We are going to sketch half of the profile that makes the cap. Click on the Line tool and click on the origin. Pull a horizontal line out beyond the standoff and click. Make a vertical line going up representing the thickness, and a horizontal line extending in towards the center. Use Escape on the keyboard to end the Line tool. We will need a center line, so I'm going to click on the Line tool and then the Construction tool. Snap a line coincident to the origin and draw a vertical line. Double-click to end the line. Next, we will add dimensions. Click on the Dimension tool from the toolbar. To dimension the outside diameter of the cap, click on the outside vertical line. Then click on the center line and move the cursor past the center. This should allow us to enter the diameter value of 22 millimeters. Dimension the height of the cap at 3 millimeters. Dimension the top line at 2 millimeters. The recess is formed by an arc projected across the center of the cap. To make the arc, we need to define both endpoints. We will use a mirror tool to mirror this top line to the other side. Click on the mirror tool in the toolbar and then click on the center line to use as the mirror line. Click on the top horizontal line and we can see it mirrored on the other side. Right-click Escape Mirror. Click on the 3-point arc from the toolbar. Click on the end of the line to start the arc. Click on the line on the other side and then pull the arc down and click. Set the radius to 28 millimeters. We need to close the region to create the profile that we can use for the revolve. Click on the Line tool and click on the origin to start the line. Draw a vertical line and click coincident to the center of the arc. Use Escape to end the Line tool. The region should now be gray and all the lines should be black as they are fully constrained. And now we've created half of the cap and a profile that we can use to revolve the feature. Use the green check to accept the sketch. Right-click and choose Isometric View. Click on the Revolve tool in the Feature toolbar. We will add to our existing part. Use the region in the sketch. Click on the center line to use as the revolve axis. This revolves that profile around the center and adds the feature. Lastly, we're going to round the outside corner. Click on the Fillet tool in the Feature toolbar. Set the radius to 2 millimeters. Click on this top outside edge to create the fillet. Use the green check to accept. Lastly, we'll change a few properties for this part. In the parts list, right-click on Part 1 and choose Rename. Name it Hub. And we'll do the same down here for the Part Studio tab. I'm going to rename and also call this Hub. To change the color of the hub, right-click on the hub in the parts list, choose Edit Appearance. Choose Blue. Use the green check to close. This creates our final part, and we can now move on to assembling our fidget spinner. In this segment, we'll assemble the fidget spinner in Onshape using assembly mates. I've opened my Onshape document called Fidget Spinner. It contains all the project parts, each in their own part studio. The bearing, the spinner, and the hub. On the tab bar, I should have a blank Assembly Studio tab. Click on the tab to open the Assembly Studio. If you don't have an Assembly Studio, use the plus in the lower left corner and choose Create Assembly from the pop-up menu. Notice that the toolbar now starts with an Insert button for placing parts in the assembly window. The toolbar also contains a variety of tools for mating parts and controlling their movement. Start by clicking the Insert button. In the insertion box, you can see the parts available in our current document. Each Part Studio tab is listed. There is an expansion arrow to the left. If you click the arrow, it shows all of the parts available in that Part Studio. In our document, we have just one part in each Part Studio. Click on the bearing to insert it. It shows up in the assembly window, but notice its color is yellow. This indicates that I can now use the mouse to drag it to a preferred location. Then left-click the mouse to place the part in the assembly window. The yellow color turns off when it is placed. Use the green check to accept. With no mates applied, the bearing still has all its degrees of freedom. If you left-click on the part and hold the mouse button down, you can still drag it around the window. Usually the first part that's placed into the assembly will be fixed so that it won't move. To fix the bearing in the assembly area, right-click the mouse and choose Fix from the pop-up menu. Now, if I click and try to drag, you will see a fix icon show up on the bearing. If you look at the bearing in the instance list, it shows a fix icon. If you need to move the bearing now, you have to right-click on the part and choose Unfix from the menu. Usually, there's only one part in your assembly that's fixed. This is considered to be the base part and is used as a stationary anchor, and other parts are mated to it. Next, notice that the only default geometry available in the assembly window is the origin. This represents the 0 point or center point of the assembly area. Usually, when inserting the base part, we want to maintain the original alignment of part with the origin. To do this, let's start over and insert the bearing again. Click on the bearing to select it and use the Delete key on the keyboard. Click on the Insert button to insert it again. Click on the bearing to insert it. Now, without dragging the bearing around in the assembly window, use the green check to accept. Right-click on the part and choose Fix without moving it. Notice the orientation of the bearing to the origin is the same as it was in its part studio. It's centered on the origin. We have aligned our base part with the origin and fixed it in assembly window. Next, we will insert the spinner into the assembly and mate it to the bearing. Click the Insert button on the assembly toolbar. Click on the spinner and then choose the green check to accept. It looks like the spinner has been placed where we want it, but there is no mate applied. So it is still free to move. Use the mouse to drag the spinner, and it still has all degrees of freedom. In order to fix the spinner to the bearing, we need to apply a mate. But in this case, we also want the spinner to be able to rotate. We can accomplish this by using a revolute mate. Click on Revolute Mate from the Assembly toolbar. Next, I have to choose 2 mate connectors to align the parts. If you hover your mouse over the bearing hole in the spinner, you'll notice that a variety of mate connectors will light up. This means they are available to choose. I want to choose the connector that is centered on the top of the spinner bearing hole. Click to choose it. Notice in the Mate dialog box, the selection has been added. Next, hover the mouse over the bearing and look for the mate connector centered on the top of the bearing. When it lights up, click the mouse to select it. The 2 mate connectors will snap together. At the bottom of the dialog box are some tools to help troubleshoot the assembly. The arrow will reverse the Z-axis orientation of the mate. The circle will rotate the X-axis and turn the part about the center. The play arrow will preview how the parts will move with this mate applied. The solve button will reapply other mates to solve any conflict with previously applied mates. This mate looks correct, so use the green check to apply. Next, we will insert the hubs. The assembly will require 2 of these parts. Click on the Insert button from the toolbar. Click on the hub and place it in the assembly window. Click on the hub again and place a second hub in the assembly window. Use the green check to accept. When the hub is mated to the bearing, it will not need to move, so we will use a Fasten mate. Click on the Fasten mate in the toolbar. First, hover on the top surface of the bearing and click to choose the mate connector centered on the hole. Next, go to the hub, rotate as needed to locate the mate connector where the shaft meets the standoff. Click to choose and the parts snap together. To accept, use the green check in the floating toolbox. Using the floating toolbox keeps the mate tool active and we can apply another Fasten mate. Turn the part to view the bottom of the bearing. Hover on the bearing to light up the mate connector at the center of the hole. Click to choose it. On the second hub, hover to find the mate connector where the shaft meets the standoff. Click to choose the mate connector. The parts snap together, but the orientation of the hub is wrong. Use the arrow tool on the bottom of the dialog box to flip its primary axis. This looks correct. Click the green check on the dialog box to accept. Right-click and choose Isometric View from the menu. Last, we need to insert 3 additional bearings and mate them to the holes in the spinner. Click on the Insert button. Place 3 bearings into the assembly window. Click on the Fasten mate from the toolbar. Use the top center mate connectors on the spinner and each bearing to mate them to the spinner. The assembly is complete. On the left, examine the instance list. Notice an instance was created for each of the parts in the assembly. Below, all of the mate connectors are listed in the order they were created. From the list, any of the parts or mate can be opened for editing. If you want to examine the assembly, we can use a section view to look inside. Click on the Camera and Render option menu, and at the bottom choose Section View. Click on the hole in one of the bearings to set a vertical cutting plane. Drag the arrow to move the cutting plane and view a cut section of the assembly. We can see that the parts have assembled correctly without interference. Use the red X to close the section view. Now that the fidget spinner assembly is complete, we can view its operation by applying animation. Look in the mate feature list and locate the revolve mate. This is the mate connecting the spinner to the bearing. We will animate this mate to see the device spin. Right-click on the revolve mate. From the menu, choose Animate. In the dialog box, note the default settings for the animation. Start value is 0 degrees. End value is 360 degrees. Steps will determine the speed of the rotation, a larger number of steps going slower and smaller number increasing the speed. For the playback, we have 3 options. A single loop. Reciprocate. Loop. Choose single. Click the play button and it rotates a single rotation. Click on the direction button and it will reverse the direction. Let's choose loop. Click play. It will continue until we use the stop button. Change the steps from 300 to 100. Click play. Notice that you can zoom and rotate the assembly during animation. Right-click and choose Make Transparent to examine the relationships of the parts during rotation. Stop the animation. Congratulations on completing your fidget spinner using Onshape. If you enjoyed this project, look for more at cadvideotutor.com.